We had just concluded with LMS algorithm for the complex case. So, let me just quickly go through those steps. There we had this thing, x n was a zero mean random process, complex valued random process, and the filtering problem was this w 0 n dot 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 say w capital N n d n y n. D n also is a zero mean complex value random process. If you subtract the error, this is E n. You define w vector as w 0 n dot 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 w capital N n. Then the departure is the filter output. We are talking in terms of w n, that is w 0 to w capital N as a coefficient, but when you filter with their conjugate values. Okay. Or alternatively, if you filter with some complex valued coefficients, we evaluate their conjugate and then get back the filter coefficients by another conjugation. Okay. So, then our equations were like this, y n was w h n x n vector, x n as usual okay. Then you find out E n as d n minus y n and then update. That is mu into x n vector E star n. You can write E h n also, because E n is a scalar. So, star or h they mean the same. There is a complex valued case. Here the optimal filter would have been what? Optimal filter, that is W opt is still R inverse P. Okay, but then you use W opt Hermitian, multiply with x n bar, then you get y n. Okay, and this W opt minimizes epsilon square, which is in this case E of mod E n square. This was okay. That is a complex elements case. In the real, this is a complex case, and for the real case, you can view real case as a special case of this, because then Hermitian or normal transposition means the same thing. Ordinary okay, means the same thing. So, in that case again you have got x n, the filter weights w 0 n dot dot w n n, y n, d n plus minus this E n, w n is and x n they remain same. In this case, so this is a special case of this, you can see now, because y n is simply w transpose n. You can write w transpose n x n, you can write w Hermitian here also, because under real case there is no question of conjugation. Okay. And same E n as d n minus y n, and w n plus 1 is w n plus mu x n vector as it is, and we write E n or E star n, they are same because they are real. So, this is a special case of this. You remember how we obtained this algorithm? We first started with the steepest descent, which was an offline procedure. Okay, the iterative offline procedure. We took that plot of epsilon square versus all the tap weights. That was a quadratic function, it has a unique minima. So, we started with one point and then went in the opposite direction of gradient, multiplying the gradient value with some suitable constant, step size mu, and then went back and forth around that optima point, and then finally converged on that. That was steepest descent. On steepest descent, what we did? We replaced R and P by some weird estimates. R by simply x n into x Hermitian n, and P by x n into E star n, which is a very wild estimate, but we said that still algorithm will work. But then since you are not giving the correct value of R and P, definitely this will not converge exactly on W opt, isn't it? If you had given it exactly, I mean the correct value of R and P, it is a simple steepest descent, exact steepest descent procedure, and it should, we can show it will directly converge on this thing, the minima point. But since you are not doing that, you are giving only a very approximate value for R and P, naturally you have to lose something. So, you will not, your filter weights will not converge directly on the optimal weights, but it will converge actually in some other way, and that convergence is its mean. That is the mean of the tap weight, this filter weight vector, as time tends to infinity. You see, everywhere along the time axis it is fluctuating, but as time tends to infinity, it will be fluctuating around the optimal value. So, that time if you see the mean, that mean will be optimum value. It will still not be optimum, but its mean will be optimum. Then we will see that okay, how to keep the variance around the mean or spread around the mean under check, under some control, in fact as low as possible. Then it will be a better kind of convergence. Okay, that is how things will evolve. So, we now do this convergence analysis, and as I said, the complex case is more general and it includes the special case also, real case, as you can see by comparing the two algorithms. Now, we will do the convergence analysis for the complex case. So, what I will do? So, this is convergence in mean, convergence analysis. You know what is W opt? That is R inverse P. Now, your W n minus W opt, that is the error vector, error in filter weight, we call it weight error vector, isn't it? Ideally, it should go to 0 as n tends to infinity, but because you used approximate values of R and P, it will not go to 0. Okay. But this will have a 0 mean, but it will be fluctuating. We call it, or denote by delta n. It is a vector, it is called weight error vector, weight error vector. Okay. Now, your equations were this is the relevance equation. You subtract W opt from both sides. What you get here is delta n plus 1, delta n plus same thing. But within this E star n or E n, say I want to write both left hand side and right hand side in terms of delta, no W. I want to remove W's and bring in delta. Apparently, it might appear to that I mean we have done our business, delta here, but actually when in this E also a W is hidden. What is E n after all? D n minus filter output Y n, and Y n is W Hermitian n into x n vector. So, there W lies. So, I have to expand it and again replace that W. D star n minus Y star n. Please see D star n minus Y star n. Okay. I am writing separately. E star n is D star n minus Y star n, same as D Hermitian n minus Y Hermitian n, because they are scalars. That is, if you replace this Y star by Y Hermitian, then this becomes what? Y n is W Hermitian n x n. So, Y Hermitian is x n Hermitian W n, that is what will come here, W n, and this W n I will replace as W opt plus delta n. From here W n is what? W opt plus the deviation. Deviation is delta n. So far so good. Okay. Now, I apply expectation operator on both sides. E of, I define E of delta n plus delta n, expected value of that, the deviation is not 0, some expected value. So, there is delta n fluctuating around something. If that something is 0, that means W n is fluctuating around W opt. So, suppose E delta n, we say it is V n. So, V n is not random. After you apply expectation operator, randomness goes. Okay. But remember, I am putting an n here because it is not really stationary, because filter weight, the weight vector, what from delta n come? Delta n is nothing but W n minus W opt. W opt is a constant. So, delta n is equivalent to W n. But W n is not stationary process, it is changing now with time by a recursive equation, LMS update equation, isn't it? LMS update equation. It is not like a pure purely random process where there is no bias on particular time axis, whether you observe mean here or there or elsewhere or variance, you will get the same thing. It is not. There is a recursive equation by which W n is generated from its past value. Okay, so it is not, you can't say that it is stationary that way, because there is a relation. That is why I am keeping an index n. If you do that, now apply E on both sides, obviously you get V n plus 1 as V n plus mu into x n d star n. If you apply E over that, what do you get? X n into d star n, P vector, cross correlation vector, mu into x n d star n, cross correlation between x n and, so you get P minus x n x Hermitian W opt. W opt is constant, so it remains outside expectation operator. So, only x n x Hermitian n, that is R, isn't it? That is R. So, we have got R W opt and another term, that term is very important. So, that term I write separately, mu x n, sorry, E x n x Hermitian n delta n. It is a product of 3 random quantities, one vector, column vector, row vector, another column vector. So, essentially a scalar, but there are 3 random quantities, isn't it? This is also random, this is random and this is random. I am coming to that later. Now, consider this, W opt is R inverse P, that is P is R W opt. So, this cancels, P equal to R W opt. So, this is equal to 0. So, I am left with only this and of course, this, right. This term is a crucial term and it is very difficult to analyze things further, and it is here the inventor of this algorithm Widrow made some assumptions, and those assumptions, I mean, you can say where they are questionable assumptions, because we can always ask questions. We can then, of course, he has a way to justify also his assumptions, but those assumptions work in practice. Those assumptions are called independence assumptions. Independence assumptions. What are the independence assumptions? Let me write here. You assume W n vector, it is statistically independent, not just uncorrelated. You know that statistical independence is more stronger condition than uncorrelated. Do you know this, or maybe for your sake I have to say, suppose x and y, okay, x and y, just see this, This is a departure from the discussion. Suppose x and y, to start with, assume they are real valued. So, if you take x and y and if they are uncorrelated, uncorrelated means is E x, E y. If they are complex valued, it would have been E x y star equal to E x into E y star. Okay, but just let us confine to real case. This is one uncorrelated. And statistically independent, if the two variables are not just uncorrelated, if I say they are statistically independent, and loosely I will always call independent, that means statistically independent only, not linearly independent. There is something called linear independence that I told earlier, that one has a linear relation with other. That is still a stronger condition, because you are assuming a specific form, not just dependence, a specific form of dependence. Statistical independent, if they are, then that means their joint probability density is individual density, product of two individual densities. You can say P x y for the joint case is P x x P y y. If I otherwise write P x into P y, mathematicians will frown. They will assume I am using the same function as though x and y have the same probability function, which may not be the case. Just to differentiate, I put P x of x, P y of y. Just for mathematics, I mean, to save ourselves from mathematicians. Okay. Now, if this is given, my point is, if they are statistically independent, that is S I statistically independent, then they are uncorrelated, not the vice versa. If they are statistically independent, what is E x y? E x y is nothing but, what is E x y? E x y is nothing but x into y into P x y x y dx dy, and the rest is very obvious. P x into x, one integral P y into y, so it is E x E y. Same thing applies for complex valued case also. But given this, you cannot get back this. Given that E x y equal to E x into U y, in general you cannot get back this. But there is one case, you see, this is not, I may not be dealing with that right now, but just for your knowledge sake, and also one purpose of this course is that you not only learn adaptive filter, through this process you develop lot of techniques to handle statistical quantities or statistical analysis. Okay. So, for that purpose I tell you that there is one case where one means the other and vice versa. That is, if x, y are jointly Gaussian. Zero mean, I am talking of zero mean cases. So, if they are jointly Gaussian, if they are jointly Gaussian, then this thing, then this will happen. Why, you know? If x, y jointly Gaussian, you know what is the joint Gaussian formula, joint Gaussian distribution of a vector? Suppose I have got a zero mean vector, this case I will handle here. In general, okay, we can extend this further. If E x y z, E x E y E z, like that we can extend further. Now, suppose consider a general case, why even x y, general multivariate Gaussian or vector Gaussian thing, Gaussian vector or multivariate Gaussian case. There, if I give you a vector x which has x1 dot dot say x n or maybe x0 to x n, and I say they are zero mean but jointly Gaussian, that means what is the density, the probability density of the vector is this 1 by 2 pi, maybe I take x1 to n, otherwise I have to write n plus 1 unnecessarily, 1 to n here. So, number of variable is n. So, 2 pi into n by 2, then determinant of, if I say r and square root of that, positive square root of that. What is r? R is, I have not completed, some more terms are there. R is E of, there is a correlation. Correlation or covariance, they mean the same here, 0 0 mean case. This thing into e to the power minus, this is the thing. Okay. In fact, if it is you can now verify if it is only one variable. If it is only one variable, then what happens? Then 2 pi into 1 by 2, 1 by root 2 pi, determinant R means R is simply a variance of the single variable square root by sigma 1 by root 2 pi sigma e to the power minus x transpose only x, only one element, that is x 1, call it x 1 square, say x 1 square, okay, x 1 square by R is only a scalar sigma square, and there will be a 2 here, 1 by 2, yeah. Yeah.
Sir, x minus x bar.
No, I am talking 0 mean, na. I am dealing with 0 mean, just to make life simple. Okay, this is a 0 mean multivariate Gaussian distribution. Okay. Now, suppose here it is said that these variables are uncorrelated. 0 mean and uncorrelated means the correlation will be 0. E of x 1 into x 2 will be E x 1 into E x 2, which is 0. Only diagonal elements will be non-zero positive number, because they will imply variance. That means R will be what? A diagonal matrix consisting of sigma 1 square, sigma 2 square, dot dot dot, sigma n square. Inverse of that 1 by sigma 1 square, 1 by sigma 2 dot dot dot. Then you can easily see, you can break it up as product of, maybe you can take it as this is a very simple exercise. What is determinant of R? Sigma 1 square, sigma 2 square, dot dot, sigma n square, square root means sigma 1, sigma 2, sigma dot dot. Okay. So, you can spread it as root 2 pi, root 2 pi, root 2 pi n times, sigma 1, sigma 2 up to dot dot sigma n, and you will have e to the power minus x 1 square by sigma 1 square into e to the power minus x 2 square by sigma 2 square, of course with the half dot dot dot. So, it will be a product of individual Gaussian densities. I am not showing that, I think is pretty obvious. Okay. So, in that case this happens. If they are jointly Gaussian, then uncorrelated means independent and vice versa. This is always true. Independence means SI means uncorrelated, but not the other way except for the Gaussian case. Another thing, for our analysis, as you will see, I may specifically mention that it is independence assumption. We will assume statistical independence of something. Why? I mean, we could have lived with uncorrelatedness. You know, when this will not work, when you have to go beyond this assumption, because you are doing some analysis, you want to make minimum assumption. So, you thought of using uncorrelatedness, you are finding that you cannot still solve, go further. Then you have to go for statistical independence. What is it that this gives and which uncorrelated does not give? Suppose this is given, but it will never mean E of say x square y is E x square into E y. It will never mean. But if this is given, then this will be true. This will be true, because x square y joint density will be still satisfying this. If x and y are statistically independent, x square and y also are statistically independent. So, you multiply with the respective joint density and then you can separate out, you get this. In fact, why only this? Then E of, if this is given, this will imply E of any f x g y will be E of f x into E of g. These are not given in books, it is not written, you have to understand. Okay. But this does not apply, does not follow from uncorrelatedness. If you are handling with this kind of cases, where x or y directly does not occur, but some function of x and some function of y occur in your expressions, you better go for statistical independence, not uncorrelatedness. Okay. Now, I come to that independence assumption. Remember, this is what we are doing. Just to give you a cue, this is where we are left with, this factor becomes 0, V n plus 1 is equal to V n plus V n minus B u into this term, and here you have got a product of 3 terms, one vector, row column vector, another row vector, another column vector. Okay. And out of which delta n is what, after all, it is equivalent to W n, in the sense that is W n minus W opt, and W opt is a constant, not random. So, delta n depends only on W n and nothing else. Delta n is dependent only on W n, fine. Now, we make an independence assumption, and this assumption might look weird, but we do. It is assumed that it is statistically independent of x n vector and d n scalar. okay, x n vector and d n scalar. Now, you know this is weird is because you look at weight update equation W n, if I put n on this side, it will be W n minus 1 plus mu into x n minus 1 vector into E star n minus 1. So, W n depends on x n minus 1 vector, but you see x n and x n minus 1 vector, they have a lot of overlap. X n vector consists of x n, then n minus 1, n minus 2 up to n minus capital N, isn't it? I mean second to nth term here is part of the first to n minus 1th term, isn't it common? So, you cannot say, so this actually is related to x n vector also. Even otherwise, there is a correlation in data, even if suppose W n dependent not on x n minus 1, but on say x n minus 10 or 12, even past data and current data vector, they have some correlation. You cannot always assume it to be white. So, that way W n has got correlation with x n, some kind of relation, okay. But we make the assumption.
Now, sir, like initially we are given dn and xn, and we have to find w such that we get dn.
Yeah, so you got an equation. You got an equation. I'm sorry, actually, because of a meeting today, it has to take place. We couldn't reach you. Sorry, I mean, here the video recording to, because today is an important lecture. Anyway, tell me, this is an equation we obtained, LMS equation.
So then, how far is this assumption correct?
No, this assumption, yeah, that is what I am saying. This assumption looks weird, because this is my dynamic equation, how W evolves with time from its past value. It gives the W dynamics, and it clearly shows that it depends on data which is part of current data vector. Then people say that this because the mu is usually small and this error is small, so in this equation this has very less contribution compared to this. So, that kind of roundabout logic, some analysis on that people do, but this is what assumption works in practice. Okay. Now, if that be so, for the current analysis I need only this statistical element of x n vector, not d n. Okay. But subsequent analysis I will need that. So, that is why I have written the independence assumption once for all, because I told you right now we will be proving convergence in mean. Afterwards, we will see how the variance around that mean can be kept under bound, can be kept under control. That is more complicated, very rigorous analysis. This analysis is mean square, this only analysis is mean. So, that time I will need independence of W n not only vis a vis x n, but also vis a vis d n. For those analysis only they have used it and it works. I am sorry, but this is how it is. They then say, if you see this book by Farang, he says that because mu is usually small and the error is small and this product and small quantity, its contribution in overall thing is less. So, that takes down that lowers the correlation, presence of correlation, all that they say. But anyway, fact is that this is an assumption they make, otherwise you cannot proceed, because what will you do after this? If on the other hand, if you assume statistical independence, see why independence and why not uncorrelatedness? Because delta n, it has got W n, delta n has got W n vector, but this term, this matrix will consist of products, x n, x Hermitian will consist of what? Products of data of the same x n vector. So, two terms multiplied of x n multiplied by say a W n component, expected value of that typically, isn't it? So, their uncorrelatedness will not work, which I told you. Uncorrelatedness only work if you have thing like this E of x y, then you can write E of x into E of y, but you have got E of x square y. You need statistical independence to write it as E x square into E y. So, that kind of situation you have here in this matrix. Each term has got a product of two data terms coming from x n vector only, that multiplied by some component of delta n, that which is one component of W n. Now, you apply E over that each term. Okay. So, that under E there will be three terms. Are you following me? This is a matrix followed by a vector, evidently it will be a scalar, but scalar component you can write as a summation of many small scalar terms. What will be a typical scalar term? Scalar term will be a product involving two data samples and one component of W on that E operator. Only if you have statistical independence valid, then you can separate them out. That is why you bring in statistical independence and not uncorrelatedness. So, under that assumption, what we have then, you can write it as E of x Hermitian, x n, x Hermitian n separately and E of delta n separately, right. That is, you can write V mu okay, and this quantity is same as V n, this quantity is same as V n, isn't it? And what is this? R. So, that means this becomes equal to V n minus mu R V n, and you can write it as I minus mu R into V n. R is a Hermitian matrix. In fact, we can assume R to be positive definite. We can assume R to be positive definite. Today the class started at 3, we could not reach you out, but I thought you cannot come because of your other class. Today there is a meeting, so I have to start. Anyway, follow the video lectures. Okay. R is a Hermitian matrix, in fact, R is a positive definite matrix, we assume. So, you remember in such case, so I just reproduce the equation here for your benefit. This is the thing, and V n was expected value of delta n. This is where we are, isn't it? You remember we discussed at length properties of Hermitian matrices and positive definite matrices. At that time I said that you can have R as some T D T Hermitian, where T consists of column vectors which are the eigenvectors of R in general complex valued, Hermitian transpose of that. Eigenvectors are mutually orthogonal. One column Hermitian times another column is 0, and you can take the norm of each column to be 1. You can assume the norm of each column to be 1. Okay, you can normalize it, you remember. So, that is why T into T Hermitian was identity, T Hermitian T was identity, we call them unitary matrices. Do you remember only this was done? T Hermitian was T Hermitian T was I. Okay. D consists of what? The eigenvalues, and for positive definite matrix eigenvalues are not only real, for Hermitian they are real, for positive definite they are also positive. This is what it is, so I replace it here. T you can always write as T T H, I you can always write as T T H. In fact, T into I into T H, you can put an I here also, minus mu T D T H into V n. You can take a T out here, I minus mu D T H V n, pre-multiply both sides by T H T will cancel, T H, multiply this by T H, multiply this by T H. So, you will get T H V n plus 1 as I minus mu D T H V n. T H V n you define as another vector U n. So, that means this is U n plus 1. Essential thing is, whenever you have an unitary matrix multiple vector, resulting vector has the same norm square as the original one. I will prove it, it is very simple. But unitary matrices like they reflect operations like rotation. By after rotation length does not change. Translation, they are all unitary operations in real life, in 3D world. Now, norm square does not change, because after all what is norm square of this vector? That is U Hermitian n U n, isn't it? Remember norm square of a vector, mod square of this plus. I think you people did not coordinate. You told me you would inform others, people are coming now.
And also maybe.
Because many are coming now. I thought you have been able to coordinate it. Today there is a meeting, important meeting, so I will be leaving at 4, so there is a class started at 3. And Joydev took the responsibility of informing everybody. So, he needs a kind of bashing from everybody else.
So no one has checked the
Anyway, norm square of U n, norm square of U n is this, you will understand this, isn't it? Any vector norm square is what? The vector Hermitian into vector itself. So, mod square of first term, mod square of second term, mod square of third term, all added. The norm square. If you put that here, what do you get? U Hermitian means V Hermitian T. This is U Hermitian. If this is U, take the Hermitian, V Hermitian T, and then UN replace T H V N, and this is I V N is so this is again. So, whenever you have one matrix, two vectors related to each other by a unitary operation, their norms are same. So, my purpose is to show, if I can show now that limit n tending to infinity equal to 0. This is what I want to show. What will it mean? That V n, expected value of delta n, V n is such that if you take the norm square, that will go to 0 as n tends to 0, but norm square of a vector 0 means each component has to become 0. You remember, norm square of a vector 0 means each component has to be 0. That means, if I can establish this, I will establish that as time tends to infinity, each component of V n goes to 0. That is, each component of expected value of delta n goes to 0. What was delta n? W n minus W opt. That will only mean that expected value of W n will go to W opt. This is your delta n. If E of this goes to 0, that means E of W n goes to W opt. So, it will converge in mean, that is what we will prove. But you remember, I told you just now, norm square of V n is same as norm square of U n. So, it is equivalent to proving limit n tend to infinity. If I can prove this, I prove this also, because both norms are same, I have just now proved, isn't it? So, now let us look at this equation. If I take the norms of, after all, what is this? This is a diagonal matrix, I minus mu d is a diagonal matrix. What kind of matrix? I am writing separately, this is a rough space, I minus mu d, this is like 1 from this I minus mu lambda 0, 1 minus mu lambda 1 dot 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 1 minus mu lambda n, some lambdas could be same. So, that times a vector, isn't it? So, norm square of, so I can write, if you take the norm square of this side, that is same as what? This diagonal matrix times the vector is another vector, norm square of that, isn't it? And norm square of that means 1 minus mu lambda 0 times the first entry of U n, square of that. So, that means 1 minus mu lambda, let me say I square U I n square I equal to 0 to n. So, simple U n each term U 0, U 1, U 2, and they are multiplied by 1 minus mu lambda 0, 1 minus mu lambda 1, 1 minus mu, isn't it? This way. It is simple, na? I am just writing this. The diagonal matrix times a vector. This will multiply first entry, this will multiply second entry, like that, and square them up. So, I am putting 1 minus mu lambda could be negative or positive. That is why I am putting, I should put a mod square, but mod square and square they are same, because they are real, square into this. In fact, I should put mod here, because component of u could be complex. So, this. Now, suppose by hook or crook I can make the coefficient 1 minus mu lambda I less than 1, 1 minus mu lambda is square rather, 1 minus mu lambda is square to be less than 1. It cannot be negative, I will not make it 0 either, I cannot make it 0, but suppose it is between 1, at least less than 1. That means, each component of, each component like mod u I n square will be multiplied by a constant less than 1. So, overall thing will be less than the norm square of u n. If all were 1, you get norm square of u n, but if each term, each coefficient is less than 1, then this quantity will be less than the norm square of u n. In that case, we can say that as time marches on, the norm square decreases, u n has so much norm square, but u n plus 1 has less, u n plus has so much, u n plus 2 has less, it will progressively go to 0. Okay, that is how it will be proved. So, I can say that limit n tend to infinity square goes to 0 if and only if 1 minus mu lambda I square less than 1 greater than 0. It cannot be equal to 0, it is a square. If you equate it to 0, it has to be equal to 0, 1 minus this. So, this has to be 1, this is a problem actually. Okay. It cannot be equal to 0 for all lambda. So, this is suppose this. So, that means 1 minus mu lambda I should be between this. So, from this side you get what? You take mu lambda I to the right hand side, 1 cancels, mu into lambda I greater than 0, but each lambda is positive and real because positive definite matrix. So, mu also has to be greater than 0. And between these two sides, if you take mu on this side, 1 on minus 1 on this side, you get essentially mu, then on this side you get mu greater than 0, on this side 2 by lambda I. Each lambda is real, that means you should have this condition on mu. This is the condition 2 by lambda max, because lambda 1, lambda 0, lambda whichever is the maximum, you have to stick to that only. It has to be less than 2 by lambda for each I. So, better take the maximum one, that will give the actual bound. So, this is the universal bound for mu. If you cross this, you are finished. The algorithm will never converge. You can just carry out an experiment in the lab, you will see it will not. Okay. But sometimes computing eigenvalue and all is a problem. So, from this we derive a slightly stronger bound. You know that R is T d T Hermitian, isn't it? So, can we say that trace of R is same as trace of D, that we have seen already, isn't it? Trace of R, that is summation of lambda i's, isn't it? Summation of lambda, which is greater than equal to lambda max. How? 2 by lambda 1, 2 by lambda 0, lambda 1, lambda 2, which whenever is the maximum I have to take that, because mu has to be less than that also. So, do lambda max only. Are baba, lambda 0, lambda 1, it is the maximum one. So, 2 by lambda only minimum 1. I have to satisfy that too. That means, it is better you stick to that only. Isn't it? That is very simple logic. Now, you see trace R is trace D as summation lambda I, which is greater than equal to lambda x, of course, because in this summation lambda I there is at least one lambda max. Others can be either positive or 0, can never be negative. If it is positive definite, others will be only positive. Okay. So, that means 2 by trace R, 2 by, if you take reciprocal, 2 by trace R is less than equal to 2 by lambda max, isn't it? So, that means, if I keep this stronger, if I keep this 2 by trace R, that will satisfy this. So, that is why in practice we stick to this one, and trace R is not difficult. If it is a stationary process, trace R after all will consist of the variances. If it is stationary, all the variance terms will be same, Toeplitz matrix, isn't it? Toeplitz, same variance, whether it is sample nth sample or n minus 1, n minus 2, all are same variance. So, just matrix number of row times the individual variance, you have to put it here only. If you choose mu within this zone, you will see it is converging in mean, but this is not enough. You have to ensure that it converges in mean square also. Mean square means, now I understand what is the physical implication of this, that okay, if you take just a single weight case, because I cannot draw for multiple weight. Suppose this is the W opt, this will mean that if you take Wn is fluctuating. So, around this zone its mean is here, then around this zone is mean is here, maybe mean is here, mean is here, mean is here, like that, but finally it will be like this. But it can also be like this, only it converges in mean. So, I understand that as time tends to infinity, the W n will have mean around mean on W opt, that is some gain, okay. At least some kind of convergence, this convergence in mean. But next we have to show is this, if you take the W n minus W of delta n here, which is a scalar in this particular case, then you have to show that this quantity, the variance, this also remains bounded, and it will be such a quantity, it will be a quantity then computable, finite, some closed form value, and they are using some parameter, we can keep the value as low as possible. So, it will be fluctuating, but within a bound. At that time, we will see if you take mu high, then what will happen? The spread will increase. If you take that mu within that range, mu on the lesser side, the spread will be less. But
it will not converge to 0.
I told you mean will converge to mean of the weight, mean delta n converges to 0, delta n, mean of delta n converges to 0. So, that is what is happening, that delta n is the deviation. This is now here delta n, whether this much, this much, this much, what is the mean of that? Mean of this is here delta n. If you subtract W n and
But variance of delta n should also converge to
that proof I have not done so far. That is a very rigorous, lengthy analysis, but I will take it up. One reason, because through that process you will learn lot of tricks of how to analyze statistical things, equations and all that. One purpose of the course also is to impart that training of statistical signal analysis. Context is adaptive filter, but as I go through that math, you will see very clever mathematical tricks here and there. So, that is a very lengthy exercise, it will take 2 days. It is a bit clumsy also, there are a lot of cross terms, this term, everyone you have to analyze, some will cancel, some will not. Finally, you will get a recursive equation of this variance, and then we will see the variance will finally converge to something, provided mu is again chosen from this range, from another range. Okay. At that time, you will see that this variance will depend on mu. If mu is large, then the spread will increase. Large means still within that range, then only it will converge in mean, but the spread will increase. If you take mu on the lesser side, then spread will be much less. The point is, the mu, if mu is large, then it converges faster. It takes much less time to hit upon this zone where the mean will be actual weight, optimal weight. If mu is less, it will take more time. So, there is a kind of trade off.
Sir, obviously, sir, it has some lengthy mathematical procedure, but from some very physical significance, it is very quite obvious. This is a convex type of structure. If we take the mu large.
No, remember one thing, that we have deviated from steepest descent. The moment I removed R and P by those things, we are not doing steepest descent, that we are not having that exact equation. That exact equation was governed by R parameter, P parameter, isn't it? That I have taken away. R and P are time varying now, x n x transpose n or x n x Hermitian n, P is x n x. So, that does not, I cannot directly use that, but still, tell me, from that it can appear to you that you will crawl. If you are really not doing this, I could have used that argument also. If you are not doing this, suppose you are doing only steepest descent, pure steepest descent, that time you can see that if you take mu small, you will be going by small steps, it will take more time, but your CO2 converge. But if you take mu large, you will be jumping to and fro so much that at least for quite some time there will be a lot of fluctuation, rapid fluctuation. But finally, again it will directly converge. Unfortunately, here it does not converge directly, because R and P have been approximated by some values. Okay. So, that analysis is called excess, that mean square error analysis. So, for that we will first see this, that suppose this is E n. We all know what is E n. E n is, now for that analysis I will excuse me, I will stick to again real case. Okay. For the complex case, they are really complex. So, W transpose n x n, but W transpose n is W opt plus delta n transpose x n. So, you have got two terms, one term is corresponding to the optimal weight, sorry, n is d n minus this. So, d n minus W opt transpose x n, what does it imply? That is when you really put in the optimal filter, that time the error is d n minus W opt transpose x n vector. So, that error is the one which will have the minimum mean square error, is it? That is why it is W opt. How was W opt obtained? By minimizing the mean square error, which is a quadratic function of the weights. So, that error is that I denote as E O n, corresponding to the optimal filter, which has the minimum variance. But you have got, since W is not W transpose, but always there is a deviation delta n, whose mean only is 0, but which is nowhere actually 0, mean only is 0. You will have another component, and that component is delta transpose n x n. Okay. As a result, if you compute this quantity, you take the whole square of this, that is, you are now finding out the variance of the error. If you take the whole square of that, one will be of course minus. So, this is that minimum mean square wala. There will be another term E 0 n into this a minus b whole square, a square minus 2 a plus b square. But E 0 n is a scalar, this is a row vector, column vector, this is a scalar, that times E 0 n. So, I can write E 0 n to the right also. First you can write delta transpose n x n, this quantity followed by E 0 n. Okay? And there is one more term E of square of this guy. Square of this guy. I am whole squaring Baba, a minus b whole square. This quantity is the best one, that is that minimum error variance attainable, because that corresponds to the optimal weight. This is the error when you have really put in the optimal weight vector W out. Then so that means this is that minimum mean square error. We can call it epsilon square mean. You cannot minimize, you cannot have any error variance less than this, minus this quantity plus this quantity. This is as it is. Now, look at this quantity delta transpose n x n E n E 0 n. If I use the delta transpose n depends on W n x n, and E 0 n depends on what? D n and x n. E 0 n depends on D n and x n. Now, if I apply that independence assumption, on this side I have got a quantity depending on W n, and this side I have got a quantity depending on x n, on which W n is independent by assumption, and here also x n and D n, on which also W n is independent. So, that means this delta transpose n is independent of this part. So, that means this quantity will be, just one more minute, I am through, E delta transpose n into E x n E O n, and I can say this, what is this correlation between the components of x n and E O n? Remember, correlation between the components of x n and E O n, that correlation is 0. You remember orthogonality I said? I had proved also that this error for the corresponding to the optimal filter, that is orthogonal to each component of x n. So, the correlation is 0. So, this will become 0 vector, which means this term will be 0. So, you are left with this and this. So, I will start from here in the next class. Okay, thank you very much. Next class is on Thursday. Okay. So, okay, that is all. Thank you very much.